And thanks for joining us today. We're going to go ahead and get started. So thank you to everyone for joining us. We are on our 7th episode of our Graph Gurus webinar series for developers, and today's presentation is Connecting Dots in Real-Time Deep Link Analysis with a Native Parallel Graph Database. And my name is Emily, and I'll be helping moderate the webinar today. So if you have any issues with audio or any problems, you can go ahead and chat with me on the Zoom interface. So before we get started, just have a couple of housekeeping items. Everyone's muted, so go ahead and use Q&A to ask questions. That is the feature in the Zoom webinar menu. So we'll save those questions for the end of the presentation, but you can ask them at any time throughout the webinar. This presentation is being recorded. If you have to jump off, we will go ahead and share that recording with you at the end of this day or tomorrow. And we're going to we've had a couple issues with Zoom. So if you're using a monitor and a laptop, there's some settings in Zoom where you can use dual monitors. That might help some people lose the screen that we're sharing. So if that happens to you, you can just Slack me and or not Slack me, but chat with me via the chat interface and I can help you fix that. So I'm gonna go ahead and get started by introducing our speakers today. Actually, no, I'm gonna tell you about the Developer Edition first. So we have two different options for downloading and installing the Developer Edition. If you want to go to our website under Developer, TigerGraph.com Developer, we now have Docker versions and VirtualBox versions for installing. So if you want to go ahead and do that now, it's a quick email that you'll get to learn how to download. So I'll go ahead and introduce our Graph Gurus today. We have Emma Liu and Huiting Su. And I'm going to go ahead and pass it off to Emma so she can introduce herself and Huiting.
Hi, everyone. My name is Emma Liu. I'm a product manager from TigerGraph. I used to work at Oracle and MarkLogic. And at TigerGraph, my focus is on the cloud infrastructure and containers, Kubernetes, as well as enterprise infrastructure, monitoring and management, in addition to the connector ecosystem. And joining me today is Huiting Su, and she is a software engineer from our solution engineering team. Huiting has a master in industrial engineering from Purdue, and she has a focus on graph algorithm, big data analytics, and machine learning. Huiting has helped many of our customers to build solutions using our GSQL language. She is our resident GSQL expert. In today's presentation, Huiting will show us a real-world demo around link analysis. So I want to talk about the agenda today. So we're going to talk about the overview for the graph algorithm, and then what is the link analysis, and why do you need real-time deep link analysis with TigerGraph? And we're going to also talk about the brand new TigerGraph GSQL graph algorithm library and why TigerGraph's architecture can be very performant to help you with those algorithms. And we're also going to show you briefly about our benchmark results. And in the end, Huiting is going to talk about the demo for our use cases. So today's session is part 3 of a mini-series on graph algorithm under the Guru episodes. We have covered PageRank and community detection in previous Graph Gurus episodes. You can find episode 5 discussing PageRank and episode 6 discussing community detection. Before we get started on link analysis, let's talk about the graph algorithm in general. We're categorizing all the graph deployment patterns and algorithm into 4 main types: link analysis, subgraph discovery, pattern matching, hub and community detection. Subgraph discovery is looking at a given graph of information of payments and claims from a group of customers and find all the relevant subgraphs. Pattern matching, you can imagine that you're trying to find similar graphs in a larger graph topology. And for hub and community detection, it's used to find the influencers in a group and find the clustering and community around the influencers. I intentionally left out the link analysis. Let's revisit the concept and definition in a later slide. As we're talking with many of our customers, some who have advanced needs on machine learning often ask us how to pick the right graph analytics tool to facilitate their machine learning efforts. How can graph analytics help you to integrate with the emerging ML solutions? In a broader stroke, from algorithm level, when you categorize your problems into supervised and unsupervised machine learning, it really depends on whether there are known graph patterns in the use cases you're looking at. In an anti-fraud case, if you're looking at for particular patterns and features, you can correlate it to some known fraud. In these situations, you can consider pattern matching, path finding, shortest path algorithm. Whereas if you're in the realm of unsupervised machine learning, you may be looking at community detection and clustering and frequent subgraphs. So I have a question to every participant. Have you thought about what exactly is link analysis? All right, raise your hand if you know the link analysis definition. Okay, unfortunately, I cannot see the poll results virtually, but I hope you had a good stretch. In a serious note, most graph analysis is a type of link analysis because graph represents the relationship between the entities. The link is the connection and the relationship, but is that all it entails? We would like to distinguish another layer of this relationship analysis. If we're only traversing the graph, it's not counted as analysis. What is important is the graph computation on top of the link relationship. It is really studying and breaking down and understanding the structure and composition of your graph topology. It presents different complexities on the level of link analysis that any computation platform can do. Can all database or graph databases carry out the link analysis you want with your topology? Not necessarily. So we categorize the link analysis into 3 different stages using the common analogy crawl, walk, and run. So for stage 1, crawling, it means identifying 1 to 2 hop relationship between entities. That's the basic leap that enterprises can achieve with graph database in a much easier manner instead of relational databases. For stage 2, you're walking. You're finding connections to more than 3 to 2 hops. You may already identify patterns such as a triangle or a circle in this stage, or you traverse a few different longer paths and finding interesting insights you didn't realize. And the final stage is running, which represents a much longer graph traversal. This means 6+ hop, and the speed is real time. And only TigerGraph among the current graph databases can achieve such performance for real-time deep link analysis. Just to clarify what a hop is, 1 hop in this chart is moving from vertex A to B, and 2 hop is from A to B to C. So why is more hop important? It provides you more information and more of the hidden information, which is hard to identify in a large data set. We'll go over a few real-world examples to discuss why deep link analysis with more hops are important. You may notice that I will keep using the crawl, walk, run analogy in this webinar. As we see, it is perfect for you to understand your use case complexity and computation complexity in the link analysis. What are some of the real-world use cases to exemplify the crawl, walk, run analogy? This is a 8-hop real-world use cases in healthcare for deep link analysis that our customer encounter. The question the use cases pose to us is, how do I detect anomalous behavior, especially if the data is sparse, such as fraud activity? So the business need here is the bad actor providers refer patients to facilities for unprofessional reasons. And anonymous behavior here comes in many forms. For example, the physician referring patients to a facility where they have a relationship with someone. In this case, the bad actor is Dr. Thomas. And the second form of anomaly could be the upcoding, which is a term meaning charging for more than a more complex or expensive service than was actually provided. And the third form is patients doing kind of doctor shopping. That means visiting multiple doctors to obtain multiple prescriptions, especially for opioids. So fraud activity data is sparse, and that's what we learned, that some of the machine learning models may not be able to produce accurate results. So the solution here is looking for alternative connections between the prescriber and physician and the referred facilities with graph analysis, graph link analysis. And you can also assign the risk rating based on the referral and the strength of alternative connections. And of course, comparing the billing across facilities to identify the upcoding and overbilling, and all these improve the efficiency for the case investigation. What is the outcome and business value from using deep link analysis here? It actually helps you reduce the improper referrals and improve the quality of care for members. Let's link back to the crawl, walk, and run example and finding out. So if you look at the chart, finding out the claims that Dr. Thomas prescribed is the first hop, and finding out the patients that Dr. Thomas is seeing is hop 2. And those are a crawling example. And traversing through this graph and hop 3, going to the claim that patient Susan is submitting to the drug rehab center, that's hop 3. And going along the graph, and you'll see that the drug center is related to a claim. And then the third party data will, the administrator will link the data with the drug rehab center. And the administrator has an address to it, to his facility, and the address will link back to Dr. Thomas. And this is what we call a fraud ring. When you see that the address of the administrator and the Dr. Thomas's address is the same address, you may find that this is actually really suspicious. And the fraud ring is established here with the deep link analysis. All right, why do we need real deep link analysis and with TigerGraph? So real deep link analysis is actually a unique TigerGraph capability. TigerGraph is the first and only graph database which can do such real-time deep link analysis. The benefits that we bring to our customers is 3 major ones. First one, you want to go deeper to your network to find new insights. Just imagine your own friend network. With one closest friend, you know his or her circle's knowledge, and then extend out, and 2-hop, you will know what your friends' friends know. So this, similarly, with more degree of separation, the knowledge in your network actually explodes exponentially. In fact, many social networks literally bank on this concept of exponential knowledge growth. So you can also drive actionable steps with timely insights and really prevent loss with the real-time insights. A quick example is that you can detect fraudulent credit card transaction on the fly with the ride-sharing companies with deep link analysis in real time. And you can prevent loss and identity theft. And the third benefit is you can capture the business moments. This is very common in e-commerce. In fact, our customerwish.com leverages our graph engine to do product recommendation, and it increased their revenue, and the ROI is tremendous. What are some of the common questions link analysis can help you answer? For example, is there a connection between customer A and customer B? What is the shortest path between location A and location B? That's common in a supply chain use case. And is driver A in the vicinity of passenger A and B around the same location B? With these common link analysis questions, with traditional relational databases, it may be challenged as the traditional RDBMS is not designed for these type of exploratory type of analytics. And using SQL statements may be difficult and slow. Whereas with TigerGraph, you can obtain these link analysis insights with our GSQL at your fingertip. We're very excited that we have a brand new open source GSQL graph algorithm library with the release of TigerGraph 2.2. This is to speed up your adoption to the link analysis. TigerGraph provides one-stop shop for you to leverage all the graph algorithm. It's open source, so we welcome contribution to our GitHub repository. We're also committed to frequent updates and adding more algorithm. So welcome input on the algorithm you would like to see in our library. Each of these algorithm is actually a GSQL query with 0 or more inputs. And it can have 3 different types of outputs. You can output to a JSON document, a CSV file, or just save it back to the vertex attributes. Find it in our ecosystem repository. The link is down on the slide. I just want to dive a little bit deeper on the nitty-gritty of these algorithms here. I want to show you guys how easy it is with our new algorithm library to achieve the link analysis. With this single source shortest path algorithm, unweighted with unweighted edges, you only need 1 line of code to compute on your topology. If a graph has unweighted edges, then finding the shortest path from one vertex to another is the same as finding path with the fewest hops. Think of the 6 degrees of separation and friend of a friend. Unweighted shortest path answers the question, how are you two related? And the 2 entities do not have to be persons. Shortest path is useful in a number of applications, from estimating influences or knowledge transfer to criminal investigation. The second algorithm is the single source shortest path with weighted edges. The finding shortest path in a graph with weighted edges is algorithm harder than in an unweighted graph, because just because you find a path through a vertex T, you cannot be certain that it is the shortest path. So a classic application for weighted shortest path is finding the shortest route to get from A to B. And this is like a planning GPS apps, for example. In general, any application where you're looking for the cheapest route is a possible fit. And now I want to stop and look at this specification here for a little bit. And when you are writing your code, you just need to tell what's the vertex you're going to start with. And the max depth here is the longest length you would want your path to be. And it will stop if you reach that max depth. And you can have display or not. And the file path is the CSV file path that you want your result to save at. And the third one is all pairs shortest path. And this algorithm seeks to find the shortest path between every pair of vertices in the entire graph. So for large graphs, though, this is an enormous task. But with our MPP, massively parallel processing of TigerGraph engine, it can speed up the computation by 10 times or 100 times. If there are 1 million vertices, then there are nearly 1 trillion output values that you're looking at. This example actually highlights one of the strengths of GSQL, which is treating queries as stored procedures, which can be called from within other queries. We're using the other single source shortest path weighted algorithm here in this particular query. The interesting clause we use here is post-accum, which is actually a unique clause for GSQL compared to regular SQL selected from statements. The post-accum clause enables aggregation and other computation across the set of vertices or edges selected by the preceding from clause. And this algorithm, triangle counting, is to identify the number of triangles in the entire graph. And this is really looking at the entire graph topology. And we leverage our TigerGraph parallelism, computation parallelism, to carry out this intensive operation. So why triangles? Think of in terms of a social network. If person A knows person B, and person A also knows person C, then we can complete the triangle if B knows C. If this situation is common, it indicates a community with a lot of interaction. So the triangle count is a measure of community and connectedness. In particular, it addresses the question of transitive relationships. If A points to B and B points to C, then what is the likelihood of A points to C? Know that it's computing one single number. How many triangles are in this graph? It is not finding communities within a graph. I want to show you quickly about the output for this particular algorithm. On the left, you will see the graph display that in the data set we compute on, there are 4 triangles that we identified in this enterprise social graph. And on the right side is the JSON output that shows the number of triangles is 4. Okay, then you might have a question. How does a native parallel database empower deep link analysis? And TigerGraph is the first and only native parallel graph database. For TigerGraph, we are has designed from ground up to handle such computation compared to our previous generation graph databases. We each automatically compute on each node based on edges, based on the massively parallel processing architecture. Each of the node and edge is a unit of storage and a computational unit as well. And the node and edges is processed in parallel, as you can find on the chart on the right-hand side. The same color nodes and same color edges are computed at the same time. Basically, all graph traversal and analysis based on what you can find can be called link analysis and computed in the MPP way. TigerGraph also automatically scales the computation so that all the computation will be spread across all threads and CPU cores. And we also have the benchmark results to show that we can perform real-time deep learning analysis in a timely fashion. This is a Twitter dataset benchmark, and this is a 2-hop path query time comparison with other first and second generation GraphDB engines. The Twitter dataset is the user follower directed graph public dataset. It has 41.6 million vertices and 1.47 billion edges. Really looking at the normalized data on the second row, TigerGraph is 40 to 63 times faster than other graph databases. This next chart shows a 6-hop comparison, which is where we start categorizing for deep link analysis. TigerGraph is the only GraphDB engine which can finish the computation for 6-hop pathfinding, whereas the other first and second generation graph databases cannot finish the query. It can run into out-of-memory issue or timeouts. Detailed report can be found on tigergraph.com/benchmark, and you can reproduce these results from GitHub repository for your own benchmark. All right, why deep learning analysis in your industry? We already talked about a previous healthcare use cases, and I want to mention a finance use cases, which is finding the false negatives in AMI, which is anti-money laundering. And we're finding the alerts missed by other solutions with Graph. The false negatives here are alerts to the fraudsters and missed by the other solutions. We're trying to see whether a new customer signed up for a particular new financial account is a fraudster. And SAR here stands for Suspicious Activity Report. In the example above, this new alert would likely have been classified as a low-risk alert under a conventional scoring approach because none of its attributes measured by the traditional scoring model displays any AML risk. However, the conventional approach fails to consider the cluster of high-risk customers that this alert is associated with. This new alert is connected to a new customer who shares the same phone number with 4 other high-risk existing customers on whom multiple SARs, suspicious activity reports, have been already filed previously. Such a hidden linkage through a single phone number would have been quite difficult to uncover using either human review or existing models or systems. Thanks to Graph, this hidden information is reviewed, and this new alert would be elevated to a high-risk alert. Let's see how many hops that we're looking at here. From new alert to new account is the first hop. New account to new customer, second. The new customer to the existing phone number is the third. And to the existing customer, fourth. And SAR, fifth. And this is what we categorize as almost a deep link analysis in the information layer. We need 5 hop here to identify the false negatives in AMI case. Now that we have talked about the finance industry use cases, Hui-Ting will demo another finance use cases for anti-fraud in credit card referral business. All right, I'm going to transition to Hui-Ting. Hui-Ting, you can share your screen. So I'm going to, the demo here will talk about 3 different queries. The 2-hop traversal, 5-hop deep link analysis, and 3 to 6-hop circle detection. So it is, going back to an analogy earlier, is the walk, run example. All right.
Thanks, Emma. Let me share my screen. Okay, please let me know if you can see the green screen. Our real-world case today is an anti-fraud use case. I'm going to use 3 queries to show different depths of link analysis. The use case is also in our test drive, so you can also try it. Click here, then we can see the Graph Studio. Let's start by looking at the schema. We have 4 types of vertices: user, payment instrument, which can be credit card or phone; device token, which is the ID of the device that makes the payment; and the transaction. There are 2 types of edges between user and transaction. User can receive or transfer transaction. There is also a referral edge from user to user. A user can refer someone else into the network. Let's take a look at the queries. The first query is called invited user behavior. A user can refer another user and receive a referral bonus. Some users may open fake accounts to earn referral bonus, and we want to detect those fraudulent users. Generally, fake accounts have few transactions, and they don't refer anyone else. So given an input user, we find all the direct invitees, then calculate the total transaction amount of the invitees and also the total number of the people they referred. If these 2 values are low, this user can be suspicious. For example, we can look at user 1. Run query, and the highlighted vertex is user 1. It has 3 direct invitees. The green ones are the transactions of the invitees. And we can also see that they have some referral activities. Go to the JSON result. We can see that the total number of people that referred is 8, and the total transaction amount is over 1,000. So it thinks that this is a normal user. The second query is called send receiver sender. This query is an anti-money laundering query. It is used to find out whether a user conducts fraudulent transactions for themselves via fake accounts. That is to say, the sender and the receiver is actually the same person. Given an input transaction, this query first finds the sender and the receiver. Then in this block, it detects whether the receiver and sender are connected via device token and payments instrument within 4 steps. For example, for the transaction 3, from this transaction, we find the sender and the receiver. So this is the sender and this is the receiver. Here, the red one. And from the receiver, we traverse 1, 2, 3, 4 hops. Same for the sender. We also traverse 1, 2, 3, 4 hops. As we traverse from the sender and the receiver at the same time, there are 5 hops in total. Here we can see these 2 groups are totally separated. So it's a normal user. We can look at another transaction. Okay, here the sender and the receiver are very closely connected. So it needs more attention as it may be a money laundering activity. The third query is also an anti-money laundering query. It detects money flow circle from a starting user. To start a user, we find all the transaction paths originated from the input user and eventually come back to the user. we set a limit for the path length, which is from 3 to 6. For example, for the user 1, it shows all the money circles from user 1 and come back to user 1 within 6 hops. You can see this large subgraph. Okay, I've showed 3 queries from straightforward one to more complex ones for link analysis. As you can see here, we have more queries, and you can try this anti-fraud use case in the test drive on our website. Hope you enjoyed the demo, and let me hand back to Emma.
Thank you, Hui-Ting. That's a really awesome demo. Let me just transition back to my slides. Okay. That's really awesome, 3 queries. I just want to recap what we talked about in this webinar. So we first talked about how real-time deep link analysis is very critical to businesses who need graph solutions. Then we also mentioned how TigerGraph is designed from ground up for this real-time deep link analysis. And we also demonstrated the GSQL graph algorithm and some of the specifications for different algorithm that enabling you to do the deep link analysis. And Hui-Ting went through a few of the use case demo, and which is very insightful to all of us. Next, let's go to question and answer.
Hi, we have several questions here, so let me open up with the first one. First question is, do you support graph sharding, database sharding for graph? The question is really about, the questioner is saying that, I guess this is similar to subgraphs, where you can support different applications based on subgraphs, which can then be recombined into a larger graph. So I'm happy to take this one. This is Gaurav Deshpande, Vice President of Marketing. Great question, first of all. TigerGraph supports full database sharding, which means you can take 1 terabyte of a graph database or even 10 terabytes and distribute it among 10, 20 machines as you need to. So if you're taking a 1 terabyte graph database, you can take 100 gigabytes and put it on 10 different machines. And we are able to run queries that go across all of these machines. So we support true database sharding. The key point to note here is the first generation graph databases like Neo4j or second generation graph databases like Amazon Neptune do not support full database sharding, which means every machine for these graph databases must contain the full 1 terabyte of graph, which makes the cost of hardware or the AWS compute cost really, really prohibitive as you scale up your graph databases. So great question. And I've got several more here. The second question is, how does the shortest path algorithm know which property to use as weights? So I'm gonna take it to our graph guru, Hui-Ting, who can answer that question. The question is, how does shortest path algorithm know which property to use as weights? Can you give some examples, and how does it do that, Hui-Ting?
Okay. So we actually have an install procedure for the algorithm. When you install the algorithm, it will ask you for the attribute name that you keep the weights. So if you, it also will ask you which vertices and which edges you want to use in the algorithm. Then after you specify that, then you just run the query.
Brilliant. Thank you for that. There's one more question that we have. Oh my God, we got several more questions. So let me start one by one. One of the questions is, what are the exemplary use cases besides the false positive that we discussed, that Emma discussed in AML? Another question related to that is, what is the typical size of graphs that you handle in AML? And how is this related to big data analytics? I think these, given that I have 22 years in big data analytics and 16 in banking, I'll take this one if that's okay with you, ladies. Perfect. We have actually an executive brief that covers AML, anti-money laundering, because we have a lot of experience and a lot of clients that are doing it. So as I mentioned, first of all, our largest graph for anti-money laundering that's in production, that's 10 terabytes. Again, that's 10 terabytes at Alipay. And that's the largest graph that we have in production for anti-money laundering AML detection. And we do run 7 and 11 hop queries to find anti-money laundering, money laundering related loops, for example, at Alipay. The executive brief, you can find it at tigergraph.com. If you go to resources page, you will find it. It's called AML Executive Brief. You'll see it right there on the page. And that has things like, in addition to false positives, it has false negatives, it has correlation, finding the hidden connections. So finding connections between new company's officials, when you're onboarding a new company as a bank client, and finding linkages with that with corrupt politicians, for example, and all kinds of other use cases that are very, very useful for AML. So link analysis is used extensively there. In fact, we have live clients that are using it in that manner to see that a new company as a part of the CDD or the customer due diligence process comes in. It has 3 officers. One of the officers has the same address, which is very similar to a politician who was recently indicted in a corruption scandal. So if you just rely on traditional database information without correlating that with the external information like TigerGraph can, you miss that connection. So this is very similar to the one that Emma mentioned about healthcare fraud detection. AML has a similar hidden relationships that you uncover during KYC, which is know your customer, or CDD, which is customer due diligence. So come and have a conversation with us. We definitely have your use case covered. And if it's a new use case, TigerGraph is flexible enough to accommodate that. How does this all relate to big data analytics? Great question. TigerGraph has handled structured data. So structured data are attributes as a part of TigerGraph. Typically, clients will use documents, process them using an unstructured content solution, extract those structured attributes, and then put them in TigerGraph. And those in turn are used for all use cases, for detecting fraud, for detecting money laundering, for finding new opportunities, for selling more products to customers, and so on and so forth. So all of that is related. I have one more question here. Let me see which of you ladies want to take that one. Do you have tools to map a relational database or other types of database extract to a TigerGraph instance? What other tools do you have? Emma, would you take that one?
Yes. So in fact, we have a equals repository, open source repository for the connectors from other databases to TigerGraph. So we have a RDBMS import to TigerGraph through, if the RDBMS has the JDBC driver, it takes that and it will import into TigerGraph. And we welcome all your contribution towards the open source GitHub as well for the connectors. So if you have requests or pull requests, and welcome your feedback and input.
Excellent. I think if we have time, we have another question in here, if that's okay. Why the relational databases cannot perform link analysis, or are they limited in that? I think you covered that briefly, Emma. But another question is, can you just talk a little bit more about how relational databases do link analysis, and what are the deficiencies in that approach from a high-level perspective?
Yeah, from high level, it's not that the RDBMS cannot perform. It can probably identify some information for 1 hop or 2 hop with the table joins. But with more hops, you will need multiple joins. And the way that RDBMS is implemented, and it stores the data in tables, making it very not performant compared to a graph database which is like natively storing the graph in a graph way. So you may easily get timeout or out of memory errors for 3 and more hops, or even sometimes 2 hop queries with relational databases. Yeah, hope that answers the question.
Excellent. I think that's about all the time we have today. Let me hand it back to our host, Emma and Emily, to wrap it up.
So really, Thank you for attending our TigerGraph episode 7. And here we have more webinars planned with the Graph Guru episodes. And we have the episode 8 already planned on December 19th. And it will talk about geospatial analysis with a graph database, location, location, location. So welcome you to sign up for the Graph Guru 8. And we're excited and hear more additional resources. And we have a new developer portal, and you can find a lot of information about our documentation and open source repository, as well as the graph algorithm library that I mentioned repeatedly in this episode. And you can download the developer edition and enterprise free trial. And we also mentioned that we have a beta version of Docker download, and you can play with TigerGraph on your laptop now. And we have the Guru scripts on the GitHub repository, and you can join our developer forum. We're also connected on all social networks. Thank you. Thank you for your interest, and thank you for your time today, and welcome your feedback.